In this video we're going to consider factorising and solving polynomials over the set of complex numbers, and we're just dealing with quadratics here, but we're going to consider cases where there's no real solutions but where we can find complex solutions. And basically we'll do that by using the fact that I squared equals -1, and that'll allow us to turn what's effectively a sum or a sum of two squares into a difference of two squares. And then we can proceed to, factorize that difference of two squares and either just leave it at that, or if we're solving, to use our null factor theorem. So let me get straight into a couple of examples. These ones sort of come from exercise 9e, although I'm going to turn one of them into a solve rather than just a factorize. So first of all, we're trying to factorize. Let's go, I'll write factorize for this one. We're trying to factorize z squared plus 5. And over the set of reals, we can't factorize that at all. But over the set of complex numbers, we can say z squared plus 5 is equal to z squared take 5i squared, since I squared is equal to -1. And now we can express that as a difference of two squares. So we've got z squared, and this one we could write as root 5i all squared, since the square of root 5 is 5. And then we can factorize it using our difference of two squares. So that would be minus root 5i, and the second factor would have a z plus root 5i. That's a reasonably simple case there, a monic quadratic, but also one without that middle term. So let's do one that's a little bit more challenging. Now this one's based on part G, but I'm going to turn it into a solve and just remind us that there is a difference between factorising and solving. So 3z squared plus 2z plus 2. So rather than just factorising that, let's solve by making an equation and letting it equal 0. So 3z squared plus 2z plus 2 equals 0. Give myself a bit of space there. Therefore, well, let's take the 3 outside here. Now I'm just going to put these, so we'll make that 2/3 z, and I'm going to leave my plus 2 out there. So now I'm going to complete the square on those two terms there. I've got a z squared plus a 2/3 z, and so the thing that I would need to add onto that is half of this coefficient here squared, isn't it? So that would be, half of that would be 1/3. So I'm going to add the square of 1/3. And now I'm going to need to subtract that as well to keep my line equal to the line above. But when I do that, I've got to remember that I haven't actually just added 1/3 squared. I've actually added 3 times 1/3 squared. So when I go to subtract, I need to be subtracting 3 times 1/3 squared. And that's still equal to 0. Let me move this over a little bit here just to line up my equal signs. Whoops, I shouldn't have done that, should I? Line up my equal signs there. Alright. So now, completing the square on what's in the brackets there, completing the square on that would be 3 outside of z plus 1/3 squared. And then we've got plus 2, and then we're going to have minus 3 over 4, isn't it? Because a half, sorry, that's a third squared, so minus 3 over 9, I should say. The third squared is going to be 1/9. Alright, let's continue to simplify this. So we're going to have 3 times z plus 1/3 squared. And I've got plus 2, which would be 18 over 9. 18 minus 3 is going to be 15 over 9. Now I'm going to leave it, I could simplify 15 over 9, but I think I'll just leave that as is for the time being. And now what I want to do is, like I did over in this problem over here, I want to turn this one into a difference of two squares. So I need to make that a minus by introducing an I squared here. So I've got 3 z plus 1/3 squared, and just realizing that I probably should have done this differently up the top, but that's alright. That was you could hear my cogs ticking there, couldn't you? So I probably should have just taken the 3 outside of the whole thing to make my life a little bit easier, but let's see if we can persist. So we're going to turn that into a minus, and let's actually take the factor of 3 back out again. So that would be 5 over 9, so root 5 over 9 I squared. Sorry, I shouldn't. Oh, I'm really not doing a great job here, Emma. Let's just remove the square root there for the time being until I take the squared outside. So at the moment we're just saying 3 times 5 over 9 is equal to 15 over 9, and negative I squared is the same as plus. So therefore we're going to have 3z plus 1/3 squared. Let's put this in some larger brackets now. So 3 times that minus, and here will be root 5 over 3I squared. Alright, so I've taken that factor of 3 out the front here, and I could now actually just divide that out, couldn't I? Because it's equal to 0, I could divide that out of both sides, but I also turned this into a whole squared term by saying that root 5 over 3 squared is 5 over 9, therefore 3, and now I'm going to use my difference of 2 squares, so z plus 1/3 minus root 5 over 3I, and z plus 1/3 plus root 5 over 3, let's make that a bit clearer, 3I equals 0. So therefore my solutions are going to be z equals negative 1/3 plus or minus root 5 over 3I. Alright, I made that harder than it needed to be, but there's factorising and solving a quadratic over the set of complex numbers.